Hi everyone. In this video, we are going to go over a specific type of addition reaction called hydrohalogenation. And we're also going to talk about someone called Vladimir Markovnikov because he did a lot of work on hydrohalogenation. So last time we saw an addition reaction where we have an alkene and we were adding a generic molecule XY across the double bond. But let's change X and Y to something more specific. So we're going to add HBr across the double bond. All right, so if we're adding hydrobromic acid across the double bond, we know that the alkene can act as a nucleophile because it's electron rich. And would that nucleophile attack the hydrogen or the bromine? So remember, nucleophiles, because they're electron rich, they will be attracted to something that is positively charged or partially positively charged. So if we're looking at hydrobromic acid, is the hydrogen partially positively charged or is the bromine partially positively charged? The hydrogen, because bromine is more electronegative. So that means the double bond or the pi bond is going to grab onto a hydrogen there, and then the shared electrons will be left on bromine. Okay, now there are two possible locations that the hydrogen could add to. Could add to the middle carbon there, or the carbon on the end. So one of those two vinylic positions. So let's draw those possibilities. So let's say the hydrogen adds to the center carbon. Okay, if it adds to that central carbon, the carbon on the end won't have enough electrons to be neutral, so it will be positively charged. So what's happening here is both of the electrons in the double bond are going towards the new sigma bond between carbon and hydrogen. So the carbon on the end is left without an electron, so it's positively charged. Okay, now what if hydrogen adds to the carbon on the end? Well, now both of those electrons in the pi bond are going to that new sigma bond, so that leaves the carbon in the middle with a positive charge. So which one of those is more stable? We have two carbocations here. Let's identify what type of carbocation we have. So in the first situation, do we have a primary, secondary, or tertiary carbocation? That's a primary carbocation. And what about in the second situation? Is that a primary, secondary, or tertiary carbocation? Secondary. Okay, so which one is more stable, the primary carbocation or the secondary carbocation? The secondary carbocation is more stable. So that will be the preferred position for the hydrogen atom. So the first situation won't happen. So let's just make a note off to the side. We're always going to form the more stable carbocation. Now, we'll also form the more stable intermediate if it has resonance as well. So remember that resonance causes more stability than a tertiary carbocation, which is more stable than a secondary carbocation, which is more stable than a primary carbocation. So we'll always form the more stable intermediate. All right, so now we also have a bromide ion that's hanging around. Remember, the shared electrons initially went to the bromine. So now that can come in and attach to, let's see if I can draw this, I'm running out of room, that will attach to the secondary carbocation position. So our final product looks like this, where bromine is attached to the central carbon. And this is what's called Markovnikov addition. So it's named after the scientist who did a lot of research on this. So this was way back in 1869. And Vladimir Markovnikov was a Russian chemist, and he was investigating how hydrobromic acid added across different alkenes. And he noticed that the hydrogen always adds to the side with more hydrogens. And then the halogen, the bromine, always adds to the side that's more substituted. And that's because you form a more stable carbocation intermediate. So what we can say in general is the halogen adds to the more substituted carbon. All right. Now, one thing to keep in mind is depending on your alkene, you might form a stereocenter when you add the hydrobromic acid across the double bond. So then you'll end up with stereoisomers in your product. So we'll talk about that later, but let's just write that down as well. So if there is a stereocenter, then you have stereoisomers. And I'm not sure why my pen decided to go bold, but it did. So we will talk about that in a bit. So let's go over an example of Markovnikov addition. And let's use a different alkene. Let's look at this alkene here. So it's a little more complex. And then we're going to add hydrobromic acid across the double bond. All right, so we know that the nucleophile, the pi bond, is going to grab onto a hydrogen, and then electrons will be left behind on bromine. And again, we have two possible locations where the hydrogen could add. So let's draw those both. So let's say the hydrogen adds to the carbon on the left, and then we'll draw what would happen if the hydrogen adds to the carbon on the right. Okay, so if the hydrogen adds to the carbon on the left side of the double bond, we end up with a positive charge on the other carbon. Or the hydrogen might add to the other side. And then we have a positive charge on the carbon to the left. All right, so which carbocation is more stable? The one on the top, right? That is a tertiary carbocation, whereas the option on the bottom is a secondary carbocation. Okay, so the second option won't occur. And again, remember we said that the hydrogen will add to the side that has more hydrogens, and then the halogen will add to the side that's more substituted. So I'm just going to erase the second option since that does not occur. And let's show what would happen when we add the bromide ion. So in this case, we're actually going to form a stereocenter when bromine is added to that positive carbon. All right, so you'll notice that the group to the left is, if we're focusing on just the positive carbon, the group to the left is different from the group to the right, and those are both different from the group down below. So that is going to be a stereocenter once we add the bromine. So the bromine can actually add from the top or from behind. So there's going to be two different products here. So the first product, bromine can add to the front or from the top, depending on how you're looking at it, and form a wedge. And then the methyl group will form a dash in the back. And then in the other option here, bromine will form a wedge. So it'll come in from behind, and it will push that methyl group out in front. All right. So what is the relationship between these two products? Are they constitutional isomers, enantiomers, or diastereomers? Enantiomers. So we only have one stereocenter, so that rules out diastereomers, which have two or more stereocenters. And then they do have the same layout or three-dimensional layout, so they're not constitutional isomers. So the only option is enantiomers. Okay, now what's also interesting is we will end up with a 50-50 mixture of these enantiomers, which is called a racemic mixture. So, are racemic mixtures optically active? So remember in 261 we talked about polarimetry, and we said that if you have a perfect 50-50 mixture of enantiomers, any optical rotation that they do have will cancel each other out. So this is not optically active because we have a 50-50 mixture, a racemic mixture. So this is just something to keep an eye on during addition reactions. Occasionally you will form a stereocenter and end up with a racemic mixture of enantiomers. All right, let's look at another example. So let's say we start with this alkene, And again, we're going to add hydrobromic acid across the double bond. So what I would like you to do is to try this problem on your own first and see if you can figure out which product or products you end up with. So you might end up with more than one, but just kind of work through it on your own first. You can pause the video, and then when you unpause, we'll go over it together. All right, so let's look at the first step. So again, the double bond, the pi bond, is going to act as a nucleophile and grab onto the partially positive hydrogen, and then we'll leave electrons behind on bromine. And again, we have two possibilities here. Hydrogen could add to the left or the right. So which side would it add to? The left, because that side has more hydrogens. And then the bromine will add to the right because it's more substituted. But let's draw the intermediate. So we said hydrogen will add to the left. So we'll end up with a positive charge on that right-hand carbon. And then we know that bromine will add next, right? So let's draw that product. And I'm just going to leave out the hydrogen on our final product here. Okay, so bromine will end up on that, this carbon here. It's hard when I can't point to things in person. Okay, but what about the carbocation up above? Is that the most stable carbocation that we could achieve? How could we make that a more stable carbocation? Well, there are some methyl groups up above, right? And remember that if possible, you could have a 1,2 methyl shift to create a more stable carbocation. So I'm going to show that in blue. So one of these methyl groups could move over, and that could give us actually, let me redraw that so it looks a little more appropriate there with appropriate angles. All right, so we'll end up with something like this, and now instead of a secondary carbocation, we now have a tertiary carbocation, which is more stable. Okay, so then we can go one step further and add the bromide ion. So now that can attack the carbocation, and we end up with bromine on the other side of the molecule. So now it's attached to that carbon there. Now, because the tertiary carbocation is more stable, that product will be the major product. The other product will be the minor product. So both products can form in this reaction, which is not ideal for chemists because chemists are typically trying to create a pure product. So they only want to produce one of these products. So if rearrangement is possible, so if a methyl shift or a hydride shift is possible, scientists will avoid that reaction because you end up with a mixture of products, and ideally we would just want to end up with one product. So let's just make a note. If rearrangement is possible, scientists will avoid that reaction. So just something to consider. So if you're ever performing an addition reaction. Okay, so what if we want to add bromine to the other side of the double bond? Because maybe we want bromine on the less substituted side of the double bond. Well, there is a way to do that, and it's called Anti-Markovnikov Hydrohalogenation, which is quite the mouthful. So we already talked about Markovnikov addition, where we said that hydrogen will add to the side with more hydrogens, and bromine will add to the side that's more substituted. So in this example, bromine added to the central carbon because it was more substituted. So that's Markovnikov addition. But if we want the opposite to happen, so if we want bromine to add to the less substituted side, so we end up with the product I just drew there, in order to accomplish that, we need to add a peroxide. So a peroxide has two oxygens in the middle. So for instance, we've talked about hydrogen peroxide before. And hydrogen peroxide is what we use to clean cuts and scrapes. It's also used in things like mouthwash as a whitening agent. So it's an oxidizing agent. But sometimes you can have other groups on the ends. So maybe you have methyl groups or ethyl groups or something on either side. And we can abbreviate those as R. So remember, we use R to indicate any sort of alkyl group. All right, so that's a peroxide. So anything with OO in the middle. So I'll just write that underneath so we remember. But what's interesting is if you just add in this peroxide, bromine suddenly adds to the less substituted side of the double bond. So a super easy solution. So again, this will be anti-Markovnikov addition. So all you have to do is just add a peroxide. Now, you don't have to know the specific mechanism for anti-Markovnikov addition because it does involve radicals. And remember, radicals are basically something that has just one electron hanging out instead of a pair of electrons. And we're going to talk about radicals later on this quarter, so don't worry about it for now. And I'll just make a note here that you don't need to know the mechanism. And I'll just add here, yet. You might have to know it in the future. But the reason is because it is a radical pathway. And we're not quite there yet. So all you need to know is if you add a peroxide, you get the opposite result from Markovnikov addition. Okay, so I think we'll stop there today. And in the next video, we will talk about another type of addition reaction called halogenation. So I will see you then.